A near 2,000-mile range fundamentally alters the structural logic of a fighter aircraft. To locate a high-value target at the outer edge of that endurance, the airframe cannot simply carry more weight. It must trade combat protection for fuel and time. This rigid engineering constraint defined the Supermarine Spitfire, designated as PR.IV, serial number AA810. The aircraft served with the No. 1 Photographic Reconnaissance Unit. It had already flown long-range intelligence missions across enemy territory, but the target that would define its final sortie was the German battleship Tirpitz. Securing that intelligence required an unescorted deep penetration flight from Scotland across the North Sea into the Trondheim area of Norway and back. The standard interceptor configuration of the Spitfire could not meet this distance requirement, so engineers stripped the aircraft down to the systems required for sustained flight and photography. Mechanics removed the heavy steel armor plating that traditionally protected the pilot and engine block. They also removed the entire armament system, including the machine guns, cannons, and heavy ammunition boxes. The reduction did not aim to make the aircraft more agile. It offset the mass of specialized internal fuel cells. The aircraft retained its standard 85-gallon internal fuselage tank. To double the operational endurance, engineers structurally modified the wings. They sealed the leading edges of both the port and starboard wings, converting the empty structural bays into high-capacity liquid fuel cells. Each modified wing held an additional 66 gallons of aviation fuel. Because the engine would have to run for a far longer reconnaissance sortie than a standard fighter mission, lubrication became a secondary mechanical constraint. To supply the Merlin through that extended endurance profile, an additional 18-gallon oil tank was installed within the port wing. This specific modification strategy created a highly specialized but critically vulnerable machine. The aircraft took off extremely heavy, burdened by the mass of the liquid it carried. Without guns, the pilot possessed zero capability to return fire. Without armor, the fuel system and the pilot were entirely exposed to incoming projectiles. The sole practical defensive mechanism for a reconnaissance Spitfire was operational altitude, outright speed, weather, and surprise. The engineering trade-off assumed the aircraft could complete its photographic pass before enemy fighters could find, climb to, or position against it. On March 5, 1942, Flying Officer Alastair's Sandy Gunn piloted AA810 on its final mission. The objective remained the movement and position of Tirpitz in the Trondheim area. To secure clear photographic evidence of the anchorage, the operational profile carried the aircraft into the Fettenfjord and Trondheim region, where altitude alone could not guarantee safety. While operating over the target area, Gunn's unarmed Spitfire entered a lethal intercept environment. During the descent, the Spitfire was intercepted by two Messerschmitt Bf-109 fighters. With no weapons aboard, AA810 could not force the pursuers out of position. The German fighters executed their firing passes against an entirely unprotected target. Reported accounts describe the aircraft being hit repeatedly until its starboard side, nose, and cockpit were ablaze. The specialized wing tanks that gave the aircraft its reach now amplified the danger. The damage quickly crossed the threshold of irreversible failure. The fire compromised the structural integrity of the forward fuselage, and the primary engine stopped entirely. The aircraft possessed zero forward thrust and was burning heavily. Gunn abandoned the Spitfire and bailed out into the freezing air. He survived the descent, but with burns to his face and hands, and was soon captured by German forces. The aircraft was left to continue on without him. The empty machine continued toward a remote mountainside above the valley of Surnadal. It was heavily damaged, without power, burning, and still carrying the residual weight of its remaining fuel and structural modifications. But it did not fall like a stone. Its final path was a shallow, uncontrolled glide toward the winter terrain. How did an unmanned, burning airframe survive a mountain collision without shattering into unrecoverable fragments? When a heavy aircraft strikes a mountain, the primary variable determining structural survival is the rate of deceleration. A direct, perpendicular strike against solid rock results in total kinetic pulverization. The exact geometry of the collision, combined with the terrain surface, dictates whether an airframe shatters or remains intact. After Gunn bailed out, the unpowered Spitfire descended toward the Norwegian terrain with the added mass of its extreme range modifications still aboard. Because the main engine had stopped entirely, the aircraft lacked the forward thrust that typically drives a crashing airframe deep into the earth. Instead, the same shallow glide carried it onto a mountainside covered by a deep, accumulated layer of winter snow. That snowpack became the deceleration medium. As the airframe hit, the snowpack compressed, absorbing much of the falling machine's kinetic energy. Because the angle was shallow, the forward momentum was dissipated over a longer physical distance rather than terminating in a single catastrophic stop. This precise mechanical interaction between the dead engine, the shallow trajectory, and the compressible snowpack prevented the total destruction of the primary airframe. The wings and fuselage were crushed and torn, but the core structural bulk of the aircraft remained largely coherent. For several months, the wreckage rested on top of this frozen layer. The heavy components were suspended above the actual ground surface, isolated by the winter conditions. This physical state was strictly temporary, dictated entirely by the changing seasonal temperatures. When the spring thaw finally arrived, the deep snow supporting the massive engine block and the crushed fuselage began to melt away. Stripped of its frozen support, the heavy structural components yielded to gravity. They sank downward, but they did not settle onto dry soil or hard stone. Instead, the concentrated weight of the wreckage drove it directly into a mountain peat bog. Entering the bog initiated a radical shift in the forensic timeline of the machine. In a standard terrestrial crash site, exposed aviation metal rapidly oxidizes. Organic materials degrade and rot due to constant exposure to fluctuating moisture levels and atmospheric oxygen. The deep peat bog, however, enforced a strict chemical boundary. As the heaviest sections of the wreckage sank below the surface of the wet peat, they entered a dark, anoxic environment. The thick bog mud effectively sealed the aircraft away from all surrounding oxygen. The severe lack of oxygen slowed many of the normal degradation processes, but it did not create a perfect chemical pause. Peat preservation depends on temperature, water level, acidity, oxygen, and the material itself. For the heaviest buried sections of AA810, the cold, wet bog acted less like open ground and more like a natural conservation vault, protecting a remarkable amount of structure that would otherwise have corroded, fractured, or disappeared. However, this preservation boundary was rigidly defined by the depth of the water and the mud. The massive engine block, the lower fuselage, and the heavy structural wing roots sank deep enough to be completely sealed. Yet the initial shallow angle impact had scattered a significant portion of the wreckage across the upper terrain before the main body came to its final rest. Sections of shattered cowlings, torn access panels, and broken instruments remained entirely exposed above the waterline, resting openly on the dry ground and exposed rock. The bog locked away the heavy structure, but what happened to the scattered components left exposed on the mountain surface for over 7 decades? Discovering wartime Spitfire material repurposed inside civilian machinery presented a distinct forensic contradiction that defined the perimeter of the recovery operation for AA810. The high-altitude impact zone had not remained an isolated, closed system. Over 76 years, the wreckage boundary had intersected directly with the daily lives of the local population. The crash site sat on a remote ridgeline, but residents of the valley below could still reach it. After the war, the exposed surface wreckage became an active resource. High-grade aviation aluminum, steel fittings, and specialized tubing held immense practical value for an isolated farming community. Locals hiked up the mountain terrain, removed exposed sections of the airframe, and carried loose materials back down to their properties. This continuous, uncoordinated removal process steadily diluted the original evidence field. The recovered Spitfire components were not preserved as untouched historical artifacts. Heavy sheet metal could become gates. Precision tubing and mechanical fittings could be adapted into pumps, churns, or other working tools. One account describes a local Surnadal motorcycle kept in service with an adapted Merlin-related part, showing how thoroughly the wreckage entered the civilian economy. This integration into the local farming economy presented a unique problem for modern aviation historians. When the official recovery project launched, securing the bog-trapped wreckage was only half of the objective. Rebuilding a certified airworthy machine required recovering as much original material as possible, including dispersed surface parts now held in private hands. Legal threats or aggressive confiscation would risk forcing the community to hide or destroy the modified parts, so the operation required a calibrated retrieval strategy. The recovery directors answered that risk with a community amnesty appeal rather than confrontation. The project engaged directly with the people of Surnadal, asking for aircraft parts to be returned voluntarily and treating the stories attached to those pieces as part of the aircraft's history. The tone was cooperative, not punitive, built around recognition, trust, and inclusion rather than threats. The community response validated the amnesty strategy. Residents voluntarily dismantled their repurposed farm equipment and handed over the historical material. The recovery team cataloged and verified each returned piece, consolidating functional 1941 Spitfire parts that had spent decades operating as agricultural tools into a unified forensic inventory. With the amnesty program completed, the recovery team shifted back to the physical terrain. The surface pieces were cataloged in the valley, but the primary mass of the aircraft remained entombed high on the ridgeline, beyond any practical heavy lift capability. A hard geometry limit dictated the physical extraction phase. A private dam road provided useful access, but it still left roughly 3 miles between the staging point and the crash site. Between the road and the bog lay steep, narrow mountain ground, forcing the final recovery into a hand-carried, pack-carried, and dragged effort. Most of the aviation metal buried in the wet mud would have to be moved off the mountain by human effort over the last miles of terrain. To work within that limit, the team broke the consolidated crash site into discrete, manageable units that one person could carry over uneven terrain. Excavation within the peat bog occurred almost entirely by hand and on hands and knees. Digging through the cold mud required extreme care to avoid damaging the preserved components with standard shovels. As the thick peat yielded loose mechanical fittings, torn aluminum skin, and severed structural ribs, the recovery team categorized and cleaned the items for immediate transport. For most of the fragmented airframe, standard hiking rucksacks became the primary extraction vehicles. Volunteers and project staff loaded their packs with recovered aviation components, balancing dense metal against the physical limits of the human body. Each 3-mile round trip required hours of effort across treacherous footing, and repeated descents turned the team into a human conveyor system. Over many days, the smaller shattered elements of the fuselage and wings reached the staging area at the dam road. The rucksack method reached its limit when the excavation exposed the densest mechanical pieces at the bottom of the site. A half Merlin engine block and other heavy components could not be treated like ordinary backpack loads. The Spitfire radiator became the clearest crisis, too heavy to carry comfortably, too important to abandon, and too vulnerable to break apart for convenience. To move the heaviest pieces, the crew engineered raw mechanical drag sleds directly on the mountain. They constructed rigid wooden frames from available timber and tightly lashed the massive Spitfire radiator to the structure to prevent load shifting during transit. Using heavy ropes, multiple team members harnessed themselves directly to the wooden frame. They forcefully dragged the massive load down the steep 3-mile trail, fighting sliding friction and the uneven rocky ground the entire way. The raw physical effort required to haul these dead weight loads down the ridgeline proved immense, but the primitive method succeeded without compromising the structural integrity of the artifacts. Through severe physical attrition, the target inventory was relocated to the access road, loaded for secure transport back to the United Kingdom, and moved out of the wild. The next boundary was not terrain, but certification. How could engineers qualify deformed 1941 metal for modern flight? Attempting to physically reshape cold, crushed heritage metal introduces severe microstructural fracturing. When historical aviation alloys are bent back into their original geometric profiles, the material stresses at the molecular level, creating invisible fault lines that render the structure unsafe for modern flight certification. Forensic assessment of AA810 therefore had to treat the recovered metal as evidence first and structure second. Reported accounts describe more than 200 machine gun hits and roughly 20 cannon strikes. This extensive projectile damage, combined with the compressive forces of the mountain impact, left key components distorted, torn, or unsuitable for any simple mechanical return to service. the engineering team faced a strict choice between static preservation and airworthiness. Leaving the crushed metal in its deformed state would permanently restrict the aircraft to a museum display. To return the machine to the sky, engineers had to guarantee that every single component could withstand the immense operational loads of flight. The engine exhaust stacks represented a critical point in this restoration path. These specific components were handmade items and had been damaged almost beyond recognition in the crash. In 1941, the original factory produced these specialized exhaust units through labor-intensive manual shaping techniques tailored to the Merlin installation and the aerodynamic profile of the Reconnaissance Spitfire. Because these exhaust manifolds operate at extremely high temperatures and channel the continuous combustion pressure of a 12-cylinder aviation engine, their structural integrity had to be absolute. Any microscopic weakness, stress fracture, or compromised weld could trigger a catastrophic in-flight fire. The team therefore had to replace the destroyed units to achieve airworthy status, but zero spare parts existed for this exact unarmored reconnaissance configuration. To bypass that parts gap, the project directors pivoted to advanced additive manufacturing through a strict digital reconstruction process led by specialists at the University of Sydney. The engineers subjected the crushed historical exhaust stacks to high-resolution digital scanning. This precise digital interface allowed the team to capture the exact dimensional parameters and original mounting bracket geometry from the deformed physical artifacts. Inside a computer-aided design environment, the engineering team combined the scan data with comparison parts. A salvaged original manifold from AA810, together with exhausts from another wartime Spitfire, helped the specialist develop a blueprint that would fit the Merlin installation. Once the digital geometry was verified for fit and function, the physical manufacturing process shifted to modern metallurgical synthesis. Using industrial-scale additive manufacturing machines, the required replacement exhaust stacks were printed layer by micro-layer. Instead of standard steel or aluminum, the engineers used Inconel, a modern aerospace superalloy formulated to withstand extreme heat and pressure without losing structural rigidity. The printed components were engineered to mate safely with the surviving 1941 engine block, providing a certified pathway for high-velocity exhaust gases through a part the original wreckage could no longer supply. With those gaps bridged by modern manufacturing, what defines the authenticity of the final machine? Authenticity in an airworthy restoration cannot rest on recovered percentage alone. Rebuilding a destroyed airframe for active flight requires a disciplined balance between provenance and airworthiness. The engineering team must preserve what remains verifiably original while substantiating every replacement part that modern flight safety demands. The reconstruction of AA810 relies on three forensic streams that cannot be treated as identical evidence: heavy structures preserved in the peat, dispersed mechanical elements reclaimed from civilian farming infrastructure, and newly manufactured components made to bridge unrecoverable gaps. The recovered core came from the mountain crater, where the peat had preserved enough original material to make the inventory unusually substantial. Public project accounts have described more than 70% of the original aircraft as recovered or represented in the inventory, but that is not the same as saying 70% can safely fly again. Later restoration reporting indicates that about 35% of the original wreckage has been reused after passing airworthy inspection, with additional wartime parts being tested and overhauled. Among the most evocative finds were original compressed air bottles still bearing 1939 test dates, evidence of how much of the aircraft's physical story remained in the mud. To build out from this recovered core, technicians must strip each Amnesty return surface, part of its civilian modifications, catalog it, and inspect it against safety and documentation standards. Components that pass can be reused in the rebuild. Those that fail still serve as evidence, patterns, or provenance. New or newly manufactured metal should enter the airframe only where the approved restoration process and flight safety require it. Beyond the primary flight structure, the restoration also extends to the intelligence-gathering equipment that define the aircraft's wartime role. The deep penetration reconnaissance mandate required high-resolution optical documentation, so the project pursued period-correct F-24 camera installations rather than empty display replicas. Apprentices and engineers at Thales in Glasgow have worked on the overhaul and repair of the F-24 reconnaissance camera fit, including two 14-inch cameras, one 8-inch camera, and their associated mounts and control equipment. The result restores the aircraft's reconnaissance role while preserving the proof limit. Not every camera component is necessarily the same item recovered from the crash site. The final assembly sequence will turn these recovery efforts into a single certified machine. Before the final mission over Norway abruptly ended its operational run, AA810 had recorded 49 hours and 47 minutes of operational flying time. The rigid engineering constraint of the restoration project is to make that frozen operational clock capable of moving again under the relevant historic aircraft approval process. The final machine is not intended to exist merely as a static, silent memorial bolted to a museum floor. It is being engineered to return AA810 to flying condition as a living memorial to Sandy Gunn and the Photographic Reconnaissance Unit.